Hello everyone, this is Aditya, and today we're going to study normalization of wave function. And if you don't have any idea about wave function, you can check out my one shot on quantum mechanics, in which I've covered each and everything related to quantum mechanics. So you can check it out. I will give the link in description so you can watch it. Now let's start with the lecture. Now assume that you have a wave function psi of x, and since we have a x, it means that we are dealing in one dimension only, right? We are not considering two dimension or three dimension right now. Okay. So you know that when you square this wave function, you take the modulus value and then you square this wave function, then multiply by dx, then this expression gives the probability of finding a particle in range x to x plus dx, right? Now this is true for continuous data. Now assume that you have to write the wave function in terms of linear combination of different phi. If you want to understand that, you can watch my video on quantum mechanics. You will understand it better, right? But basically, if you are writing psi as the sum of these expressions, right? If you know this is the linear combination of different states, right? So in that case, the probability can be written as Ci mod square, right? This is for discrete data and this is for continuous data, right? Okay, so far so good. Okay, now what do we mean by normalization of wave function? Now first of all, we will be dealing with realistic wave functions only. We won't go to unrealistic wave functions like the Dirac delta function and something like that. We are not going to consider that, right? So basically, now suppose this is your probability distribution graph. Okay, this is psi square, right? And this is x, right? And suppose the graph is going like this, from A to B, it is going like this, correct? Just assume it, okay? Correct? Okay. So what is the probability of finding the particle in this range A to B, right? Let's calculate this. It will be integral from A to B, right? Okay. And of course, I have taken here psi square because if you take psi, then you know that psi can be a complex number also, right? Means it is generally a complex number, so that is why it will be difficult to plot on a real axis. So that is why I assumed it over psi square, right? So the probability will be given by psi of x modulus square dx, right? This is the probability of finding the particle in A to B, in the range A to B, right? Okay. Now this is called, this whole procedure is called Max Born's interpretation, right? Basically the probability function over here, right? Which we are dealing, that integral of psi square is giving the probability of finding the particle in that interval, right? Now what is the probability of finding the particle in this complete axis? Let's see it. Dx, it should be equal to 1, right? Correct, it should be equal to 1, right? Okay, since it's obvious that we will find the particle somewhere in this universe, and of course since the universe is assumed over here to be 1D, so of course it is obvious we'll find somewhere particle, right? So of course probability should be 1, right? Correct. But sometimes what happens is that when you integrate, when you assume this wave function, when you integrate it from negative infinity to infinity, suppose psi of x square dx, you get a value other than 1, right? Suppose you get beta, right? Okay, beta gamma, whatever value, it is just a constant value, right? It is not a function of anything right now. Okay, so in this case what we do is that so in this we define another wave function, suppose psi 1 of x, and we write it as psi of x divided by square root of beta, correct? We can write it like this. Now this is one value of psi 1, right? You can get psi 2 as like this also, negative psi x by root beta, correct? This is also valid, right? Now there can be multiple such wave functions defined, which will give the integral from negative infinity to infinity, suppose psi 1 of x whole square dx as 1, right? Correct. Do you know that why it happened? Why? Because when you substitute the value of psi 1, it is psi of x divided by beta, and it is mod square dx is equal to 1, right? So 1 upon beta multiplied by what is its value? Its value is equal to beta multiplied by beta. So it is equal to 1, right? So we have normalized the wave function. We say it like this. So instead of writing this, we say it that 1 upon beta negative infinity to infinity mod psi of x whole square dx. This is called normalization, right? We are basically finding a constant over here, right? So that we can multiply it to get the probability as 1, right? So this is the basic idea of normalization of wave function. We basically multiply the original wave function by some constant, or we make some adjustments like this, right? Of course, we found two wave function, there can be multiple other wave functions. Now in the case of unrestricted wave function, how do we normalize that? Basically in this we are setting it equal to some constant. In this we are just multiplying by constant. In that what we do is we multiply it by some function, right? And that is not a topic to be discussed right now, but this is a basic idea that what and how the things are happening, right? So I hope that you learned something new from this, maybe, right? So of course you can define multiple wave functions like this, right? Correct. And similar in this case also, if this is telling the probability, it means that sum of all mod ci square must be equal to 1, right? Correct. Since the sum of all probabilities over a sample space must be equal to 1, right? Correct. So it means that over here it is equal to 1. So this is also normalization for discrete data, and this normalization for a continuous data, right? For this data, and this for discrete data, right? So I hope so that you enjoyed this video. If you did enjoy this video, then please do like, share, subscribe my channel, and you support this video. Bye bye. Take care.